All right, there we go. Welcome to United Astronomy Clubs of New Jersey. We are here once again in Jenny Jump State Forest in Hope, New Jersey. So, just to give any last minute stragglers who didn't realize the talk actually starts at 8 p.m., a chance to get in, get parked, pull up a bench, fold out their seat, or whatnot. I do want to welcome not everyone who's joining us here, but also joining us online because that is right. We do live stream these to both Twitch and YouTube. So if you're ever looking for something to watch on a Saturday night when you haven't managed to find yourself in the state forest, do feel free to join us there. Hit those like and subscribe buttons. It does help us get our love of science, astronomy, and space out to as many people as possible. In addition, you can also check us out on our website, uacnj.org. You can find a list of all our upcoming talks and as well as the past talks we had this season. It's also a great place to find out about our member clubs because we are actually a club made up of other clubs. And one of the easiest ways to get into astronomy is to find and join that local club. If not only for that ease of access of being closer to your own home, but also because the tips and tricks they'll have for those secret spots where it's like, wow, you can get a really nice view of these planets over here are much more applicable because the tips and tricks I know for out here in Warren County, New Jersey, aren't very effective if you're trying to view stuff out closer to New York City. That being said, you can also check us out on our social media pages, our Facebook, Instagram. We have a Discord server. All great places to keep in touch with us, ask questions, and find out any other interesting tidbits we're up to, such as fundraising for the new observatory we're going to put up to house the 25-inch telescope donated by Alan Midkiff. So we are fundraising for that. I do have some flyers and whatnot around, and we're hoping to break ground this year to house that, finally have that telescope back up and running. With that, since it looks like we're pretty well parked and situated and found our way down here, a little bit of a safety briefing, and for people who end up sneaking in later, they'll have to sit through it too. If you guys here need to use the restroom, that is the porta potty in back. It is big, it is blue. During the dark, you'll see it's illuminated by red for ease of finding. It is to my left, your right. In addition, we have a little museum and gift shop area. Feel free to check that out. It has a display of meteorites and telescopes and other cool astronomy items. We have our observatories out there. Each of those sheds has a roll-off roof, and the ones with the roofs rolled off are open, and assuming the cloud situation works out in our favor, we will be stargazing after the presentation. Speaking of after the presentation, it is going to get dark. It is a state park, although it's going to be slightly less since we are dealing with, I believe, full moon situation or a full moon adjacent situation tonight. That being said, it's still going to get dark. So when we go to leave in our cars, we do ask you do use your headlights. Being able to not only see people running around, but also see the fact that there is a car coming at us helps us stay safe and not find ourselves in a trip to the emergency room. Let's face it, we all should avoid the random trips to the ER. No one wants them. No one needs those medical bills. That being said, any flashlights, or like our cell phone light, if we may be needing to use those to get around, I do ask you try and keep the lights pointed towards the ground because we don't need to accidentally blind people by doing flashlight rave tricks with the latest greatest 100,000 lumen monstrosity off of Amazon. I've been there, done that. It's not fun when you lose all your night vision. That being said, I never usually have any since I'm monitoring chat and therefore looking at a screen the entire time. All right. You're not here to listen to me blabber on. You're actually here to learn about the unstable fluid universe and how your coffee is like a supernova with Dr. Chirag Skolar. Uh, it helps if I'm reading the correct bio. Uh, Dr. Skolar is a computational plasma physicist working at New Jersey Institute of Technology. He got his bachelor's degree in mechanical engineering at Boston University and his PhD in aerospace engineering at Virginia Tech. He is interested in all things plasma physics, with special focuses on plasma material interactions related to renewable energy nuclear fusion devices, plasma turbulence development in Earth's ionosphere, and improving remote sensing capabilities of non Maxwellian plasmas. And if you're like me and very confused, don't worry, he will answer all of your questions after the presentation when we have a Q&A session. And with that, here he is.
Thank you very much for the introduction. Hi, everyone. I'm glad we've got a good group of people here today. Here's hoping that the clouds stay away and we can get some really good observing tonight. uh, every time I look at the night sky, I feel incredibly humbled, and as I feel we all should. We're little apes on a small rock hurtling through the vastness of space. And during my PhD and during my research, as I was learning more and more about the work I was doing in ionospheric turbulence, I made a realization of something that I thought was really a profound beauty that I found in the universe, of things that occur on a regular, mundane, everyday human life scales, things that we do, things that we see that we might not even think about or in relation to the universe, happens in a very similar, if not the same way, on the grandest of astrophysical scales. And my hope today for you with this talk is to convey some of that so that maybe you can take away some of this beauty, and maybe the next time you're taking a sip of coffee, you'll think, the way that this coffee was made is the same thing that's happening in supernovae. So before I get to the meat and science of my talk, I have for you a very famous painting that we may have all seen in our lives. This is The Starry Night by Vincent van Gogh. It is it's a depiction of a small, lovely town in France with these beautiful rolling hills, and you've got the moon, you've got stars, you've got Venus, and we see these like beautiful brush strokes, these beautiful swirling patterns and vortices, and I just want to take a second to just take this painting in, because what I find really cool is the same things that happened here on this planet that the artist used as inspiration to make this painting that has captivated us for over 100 years is what I'm going to be showing you in these cool images and videos, and you will see things that look similar to what we have over here. So I think it's just a really fascinating and great way to connect some of the art that we see to what we actually see in the universe, and just I find science beautiful. I'm a scientist, so I'm hoping that we can all see it in a fairly similar light. So the title of my talk is An Unstable Fluid Universe. So we all know what these words mean from a very colloquial sense, unstable fluid universe, but what I want to get at is, what does it mean when a physicist or an engineer says these words, specifically the words unstable and the words fluid? So we're going to start with the word fluid. So first, the question is, what is a fluid? And to get to that, I want to look through all the states of matter. Can everyone yell at me? What are the three states of matter that we learned in school? Solid, liquid, and gas. Yeah, those are the three states of matter. So we've got your solids over here. They're generally in the crystalline structure. They vibrate a little bit. For the most part, they stay exactly where they are. An example is a bunch of rocks. You have your liquids. Liquids they take the shape of your container, but in this case, they're held down by gravity. They can move a lot, but they still have a lot of collisions in them. And the classical example is water. And you've got gas. Gases will take the shape of your entire container. The particles move around a whole bunch. They collide a little bit, but not as much as in liquids. And a great visual example here is steam, but best example is the air that's around us, right? So my question to all of you is, which of these are fluids? Any guesses? All of them. That's a good answer. Any other answers? Okay, well, we'll stick with all of them. That is right with a caveat. It's the answer typically is going to be liquid and gas. Liquids are fluids because just the way that they behave is your quintessential fluid. Like when you get sick, the doctor says drink your fluids. You go drink your Pedialyte or whatever. So you take some sort of liquid in. Gases can also be considered fluids because they behave in a very similar way. So the typical answer is liquid and gas. But like the asterisk is there are very few situations where yes, you can model solids even as fluids. In certain areas where you have really large compressive forces like geologic processes in the earth, you can model certain solids there as fluids, and even in certain nuclear fusion applications that I'll be showing later on, you can model the solids over there as fluids just because there's really large compressive forces. But generally, if we're going to take a fluid mechanics class in undergraduate, they'll say liquid and gas is the answer. But the work that I do is in plasma physics, right? So plasma is considered colloquially the fourth state of matter. So we could think of it as an ionized gas. We can take the gas that we had in the previous slide, which was a bunch of neutral particles bouncing around, but now through some mechanism, whether it's a large electric field, a lot of energy that you put in with temperature, maybe there's photon bombardment, you can excite an electron from that neutral particle and in some way rip it off, and now you have a sea of positively charged ions and negatively charged electrons that are all interacting with each other in very complicated and complex ways. And this is one of the reasons that I find plasma physics so incredibly fascinating to study. And plasmas are ubiquitous, not only in different ways that affect our lives, but also in the universe. So here are a few examples of plasmas that we may have seen or at least encountered before. On the very top here, we have the aurora, which is a very great visual representation of the plasma that naturally exists in our upper atmosphere. I don't do any research in the auroral area, but I do research in other aspects of the ionosphere. Then on the top right, we have lightning. Lightning is just an ionized gas. You've got this discharge between your cloud and the ground, and the discharge goes through the neutral atmosphere that then becomes ionized due to all that all the energy. On the bottom middle, we have the sun, which the sun and every star is a big ball of plasma. They're held down together gravitationally by their own gravity, and then in the center they undergo a whole bunch of nuclear fusion reactions that gives them that emits all of the light that makes its way to us to give us the life on our planet. And it's a very, very fuel-rich energy source that we're also trying to harness from the perspective of like consider the holy grail of renewable energy. So nuclear fusion on the bottom right here is the inside of a tokamak, which is a machine device that's being developed still. It's in the research phase of how we can actually harness that nuclear fusion energy like on the sun, but in a safe, sustainable way. I'm not working on that aspect of nuclear fusion. I'm working on a different aspect, but it's a very good picture and example of that. And on the bottom left here, we have a picture of plasma etching, which is a manufacturing process. So a lot of the chips that go into the computers and phones and whatever other electronics we have, they're very often made by plasma that's etching the circuitry right onto the chip. So it's very ubiquitous in so many aspects of our life, whether we realize it or not. And from the perspective of the universe, I'm doing an astrophysics talk here. So from the perspective of the universe, it is the overwhelmingly most abundant state of matter, like 90 some percent. Regular matter, I'm not considering dark matter, but in terms of regular visible matter, it is the overwhelmingly most dominant state of matter. So I've said liquids are fluids, gases are fluids, and plasmas are fluids. So what does it actually mean when I'm saying the word fluid in that regard? And what it means is really it's a way that we can model the universe. It's a way that we can model whatever problem it is that we're trying to look at, and they all follow the same general mathematical formulation. And this is one of the things that I find really incredibly beautiful in that we can look at things, and I'll show in the next slide, things on regular human scales that we can model with fluids, but we can model these grand astrophysical things with the same exact general set of equations. Now, sorry, excuse me, I don't expect everyone to understand what these equations are, but I want to give a little idea of what these equations are fundamentally saying, because I really think it's very powerful uh, what's being stated here. So these are the Euler equations. These are the simplest set of fluid equations you can have. And really what they're saying is a conservation of mass equation, conservation of momentum, and conservation of energy. These are standard conserved quantities that we learned about in our high school physics classes, that these things are conserved. So what does it mean when we have these equations? Well, I've also color-coded different aspects of what's in these equations. So on the left-hand side here, with this curly d over curly dt, that's a time derivative. So what that's really saying is that whatever conserved quantity we have here, we're looking at how that quantity changes in time. So if that quantity is going to change in time in some way to maintain conserved overall, well, then it must change in space in some way. So if in this region there's less of some density, well, that density had to go somewhere, so maybe it's over here now. And that's what the second column is, with this triangle with the dot on it. That's called a divergence. That's looking at how these quantities change over space. Uh, but also we have the pressure terms here, which are really just looking at internal collisions. So part of the reason we can look at this fluid approximation is if there's sufficient enough collisions between particles, we no longer need to look at each individual particle and model it that way. We can say, well, let's look at statistically the large average of these particles, the density, the large bulk particles of the density, the temperature, drift velocity, things like that. Those are good enough to get us an understanding of what's truly going on. And the pressure effects can account for all of those internal collisions. And the last bit is just additional sources. So this is kind of the general set of equations you could start with. Then you add things depending on what it is that you care about. So for example, viscosity is something that might be important. So for air, the Euler equations do a decent amount of decent job for this. But if you wanted to model honey, for example, honey is a very different type of fluid. It's very viscous. So you need to make sure to include viscosity to be able to understand the effects of what's going on with honey for whatever you care about. And if you have viscosity, you get the very famous Navier-Stokes equations. And the work that I do in plasma is you got charged particles. So they're going to be affected by electric and magnetic fields. So you could add electromagnetism as source terms here. In astrophysics, you can add gravity, because so many things are gravitationally bound. And this list can go on. I've got chemical reactions and radiation here, but you can just keep adding things depending on whatever it is that you actually care about looking at. And then you can have this for multiple different species. So in air, we know that air is primarily nitrogen, a little bit of oxygen that we breathe in, a little bit of carbon dioxide we breathe out, and a few other trace elements in there. If you cared about each individual species, you would have a set of these equations for each different one. In plasmas, that often typically becomes you got one set for ions, one set for electrons. So you solve all of that together, but then you need to close it maybe with some of other equations depending on what you have in your source terms. So in plasmas, one typical example is Maxwell's equations for electromagnetism. So you can, if you couple all those equations in, you can see how the plasma affects the electric and magnetic fields, and how the electric and magnetic fields affect the plasma all together, and you solve that. So to me, this is really like the fundamental beauty of what I'll be showing you, is that the reason that all of these other things, all the cool pictures that I'm going to show you, comes down to this kind of mathematical formulation, that they all follow this same general formulation and behavior. So gases, liquids, fluids can all be looked at as gases, liquids, plasmas can all be looked at as fluids, but still not all the time. And the way that we can look at it is really we need to make sure there's enough collisions in whatever you're looking at to model it as a fluid. If there's not, then you can't model as a fluid, and you actually have to look at each individual particle because it matters. But if they're all colliding, then statistically you can take like a large scale average and get a good understanding. And the way that we quantify this is something called the mean free path. The mean free path is the average distance a particle will travel before it undergoes a collision. So over here, we have a diagram. There's some particle. It started out on the top left. It undergoes a bunch of collisions and ends on the bottom right. And if you take the average of each distance between each of those collisions, that is the value that I'm talking about as your mean free path. And if you're looking at things on the order of that or smaller than that, you cannot look at whatever you're looking at as a fluid. If you're looking on scales larger than that, well, there's been enough collisions that you can actually model this as a fluid. And that's a very simplified equation for this is on the bottom over here. Lambda is the symbol we use for the mean free path, is equal to 1 over n times sigma times the square root of 2, where n is the number density. So that's the number of particles per some volume. So you could think of this as, suppose I was in a room and I had two balls, and I threw those two balls in a random direction. what's the chance that they're going to hit each other? Not very high. But now suppose I'm in that same room and I have 1,000 balls and I threw them all in random directions. Well, the chance that those balls are going to hit each other is now much higher. So that's what that term is saying. And then sigma is the collision cross section. So we could think of this as the size of the particles. So imagine I had same room and I had 1,000 small balls. Yeah, some of them might hit each other, but now if I had 1,000 large balls, we would imagine they're more likely to hit each other just because they're larger. So that's really what that's saying. And I just have this table here showing a really interesting list of different media that we could look at. Every single one of these has been modeled using the fluid equations, but they're all so incredibly different. And the middle column is the mean free path. So if you're looking at scales on that or smaller, you cannot model this as a fluid. But as long as you're looking at scales larger than that, it works. And on the right is things that maybe our human brains can begin to understand. So let's go through this. Water, the quintessential fluid, has a mean free path on the order of 10 to the negative 10 meters, and that value is actually slightly smaller than a water molecule. So a water molecule will, on average, travel smaller than its own size before it collides with another water molecule. And that's why that's why liquids are so easy to model as a fluid, because they're just so highly collisional. We can take air at standard temperature and pressure, so 32 degrees Celsius and 100 kilopascals. You get something on the order of 10 to the negative 8 meters. That's about the size of a bacteriophage virus. So if for whatever reason you cared about something smaller than that, you can't model air as a fluid. But still, it's very small enough that for most things we care about, air is a great fluid example. Let's go up in altitude a bit. We could look up 8.8 kilometers and look at the air on the peak of the mountain Sagarmatha, which in the west is called Mount Everest. That's only gives us an extra order of magnitude, right? We know that at the top of this mountain there's a region called the death zone, right? You got to bring oxygen tanks and everything, so there's less air there, but still that doesn't change the mean free path very much. It's still very, very small. It's on the order of the diameter of SARS-CoV-2, the COVID-19 virus. Let's keep going up higher. Low Earth orbit, 300 kilometers in altitude. This is where where I do a lot of my research in the ionosphere. That gives you something on the order of kilometers. Right, this is about the size of Central Park. Right, a particle is moving on the average of Central Park before it hits something. Let's change speeds a bit and go to the center of the sun. Center of the sun, very dense. All of the sun's gravity is pushing everything together. You end up with mean free path of 10 to the negative 14, about the size of the uranium nucleus. Very, very small, looking at actual nuclear levels. If we go to the surface of the sun, or what's called the photosphere, you end up 10 to the negative 5. That's about the size of a white blood cell. If we go even higher, let's go to the interplanetary medium. This is the stuff in the solar system in between our planets. This gets you to 10 to the 10 meters. That's half the distance from the sun to the Earth. If we keep going even beyond that, we go to intergalactic scales, right? We talk about space as a vacuum, but there's stuff there. There's just not much stuff there. On the interstellar medium is 10 to the 14 meters. That's 10 times the distance from Voyager 1 to the Earth, about 10 times the size of our solar system. We keep going up. We go to the intergalactic medium, 10 to the 17. That's the size of the Orion Nebula, which I just find crazy. A particle is moving this distance about the entire length of the Orion Nebula before it hits another particle, and yet all of these are fluids, and we can model them using the same set of equations. So I went at length about fluids. Let's talk about what I mean by the word unstable. The best way I always like to discuss this is something that we're all very familiar with, is a simple pendulum, especially if you loved going on swings as a kid. So if I have a pendulum set up like this, and I run this video that I did a simulation of, I think we're all very familiar with what's going to happen. It's going to go down, and it's going to settle at the bottom. This bottom point is the stable equilibrium. But a pendulum has two equilibria. There's this bottom stable one, and there's this top one over here. And these are actually videos, so they're going right now, but they're not doing anything because they're stable. In the unstable equilibrium, if you're perfectly vertical, it will stay that way forever. But the reason it's unstable is that if you give it an ever so slight kick. So here I have this, and I'm going to start this video now. So what I did in this is I gave this vertical pendulum a very slight kick of 10 to the negative 13 degrees, incredibly small. And what we're going to find is any second now. There we go. It begins moving. Right, that's all it took. It took me a very, very tiny kick. Because it was unstable, it went on its own and it gained all of this energy and ended up at a stable equilibrium. So this is what we mean by the word unstable is in some way, through some configuration. It's usually in fluids or in other aspects of physics. It's more complicated than something as simple as this, but it's the general idea of you give it a small little push, and it just kind of goes on its own. Uh, and usually it ends up at some sort of other stable equilibrium after that. So in terms of the actual fluid and plasma instabilities I'm going to be talking about today, there's so many of them, but I'm going to be talking about the Kelvin-Helmholtz and the Rayleigh-Taylor instability. And the reason for that is I've done research in these, so I'm very familiar with these instabilities. They're instabilities that, whether you realize it or not, you've seen many, many, many times in your life. They're instabilities that are seen all over the universe in many different scales, and they're also just really pretty to look at, so it makes for a very good public outreach talk. So we have here the Kelvin-Helmholtz instability, which is an instability that's set up in this sort of formation where if you have some fluid sitting on top of another fluid, and they have a velocity shear, so the difference in the velocities between these two fluids is different. If that's the case, you end up with first this linear regime where the interface is going to grow a little bit, and then you see this interesting helical vortical type roll up in the interface, giving us the Kelvin-Helmholtz instability. Now, just because you have velocity shear doesn't mean you're always going to be Kelvin-Helmholtz unstable. It gets damped by things like surface tension or collisions or viscosity, but generally velocity shear is what you're looking for, and the other terms will play some roles in changing the way that the KHI might look. And this is something that is found ubiquitously in our lives and throughout the universe. So can I ask the audience a quick question of, could you maybe give me an example of what you think might be a KHI you've seen in your life? Yeah, wave on the ocean is a great example. I've got a whole bunch of examples here. The top left is exactly that. You got your waves on the ocean. The water is moving at some speed, the air is moving over at a faster speed, and it gives you the waves that we see on the beach. When you're further away from the shore, you just kind of get a few bumps. Like that's like the linear regime that I showed you earlier. But then as you get closer to the shore, you get into this very highly nonlinear regime, and you get to the wave breaking and some of that vortical structure. Yeah, they also happen in clouds. Sometimes you might see them. Here is an example of an image over Hartford, Connecticut, and we can see these billowing Kelvin-Helmholtz instability patterns. They're not quite as nice as like the diagram I showed in the previous slide, because the effect of some of these damping effects like viscosity can make some of the spirals kind of bleed into each other a little bit. But keep that shape in mind, because we're going to be seeing that shape in a few other spots. And maybe after the talk, it'll be easier. But it's hard to see. I was on a plane last year, and I was looking outside, and I actually saw Kelvin-Helmholtz instabilities right at the edge of my plane. They're like right here. But again, it might be hard to see back there. Uh, but yeah, you can find Kelvin-Helmholtz instabilities in the clouds, which is really cool. But what was I found to be absolutely fascinating is, here's this really cool video. I was actually visiting my sister-in-law's house over Christmas, and they were cooking something, and you can see the steam goes up, the steam hits the microwave, so it can't go up anymore, so it now has to go to the sides. Well, now the steam is moving to the sides, the air around it was not doing anything, so you get these beautiful Kelvin-Helmholtz instability roll-ups, just in like, very standard thing that you might not even notice to realize. So I'm actually gonna do it in slow motion, and it's like just take a look at some of these small scale features, because I'm about to show a simulation that solves the fluid equations that shows very similar sorts of behaviors, and you find these very similar sorts of patterns in some really cool astrophysical diagrams I'm going to be showing. So here's a simulation that's running right now, and we can see this is the beginning of the linear phase. You can see a few little bumps forming, like the large bumps. Then we see these little Kelvin-Helmholtz instability ripples forming, and we're going to be seeing these really cool, interesting, and intricate patterns about how the different instabilities will interact with each other. And then now we can see, like over here, and there's going to be a few ones over here. You see these little bumps over here. You've got the different Kelvin-Helmholtz instabilities are creating more and more little velocity shears. So you get little Kelvin-Helmholtz instabilities on top of more, on top of more, on top of more. So it gets us this really neat like fractal type pattern. And this is what when we get to things like turbulence and looking at the energy cascade of how we get from these large scales to the small scales. So hopefully you saw some similarities in this is a lot slower, of course, than the video I showed previously, because that's what was happening in real time, where this is trying to explain some of those really fast dynamics here. So keep this image in mind, because the next slide I'm going to show you is a video of Jupiter, and it's going to look very similar to this. So here is footage of from Voyager 1 as it was moving towards Jupiter. It took one frame every 11 hours, which is about the length of one day on Jupiter. Jupiter spins very, very quickly. And because of this, it actually makes it very ripe for Kelvin-Helmholtz instabilities because of the way it's a gas giant, and then because of the way they rotate, they actually end up rotating at different velocities depending on where you are in latitude. So you end up with these really interesting band structures and these really interesting Kelvin-Helmholtz type instabilities forming throughout throughout the planet. So it's just really beautiful and fascinating to look at, and how just the similarity. I'm gonna stop. I'm gonna play it again. Yeah, the similarities between the simulation that I just showed and what's actually happening, in real life on the planet, and it's really fascinating. So now this was something that was taken in the 1970s when the Voyager missions were happening, or when they were visiting Jupiter. But we have some better footage from there. Here we have footage from the Juno spacecraft taken in 2018. And this is a still image, but we can see all the beautiful different effects of the Kelvin-Helmholtz instabilities. Certain ones over here that are kind of like the billowing damped ones. There are these larger ones over here, and there's smaller ones that are just showing up all over the place and interacting in these really, really interesting nonlinear ways. And you look at this, and then you look at the Starry Night, and you can see the similarities between the two, about how things on our planet are happening in these really cool ways on other planets and in the universe. So, and Jupiter is not the only planet that exhibits this sort of instability in the same way. We can also see this in Saturn as well. So for the exact same reason, Saturn's a gas giant, it's spinning, and it has these different bands. It's not quite in the same way as Jupiter. This is taken from the Cassini spacecraft. And we can see that the KHI exists in Saturn's atmosphere too. So it exists in planets, but it also exists in our sun as well. So here is, I'm going to have a video that I'm going to play in a second. On the bottom left here is a picture of our sun, and there's going to be a coronal mass ejection, which is an ejection of a large quantity of plasma from the sun. So if I start the video, there was a bunch of plasma that just ejected from the sun in the top left direction, and this plasma is like larger than the Earth type of scales that we're looking at. So now you have a bunch of plasma that gets ejected, that's moving away from the sun at fast velocities, and the stuff around it isn't moving. So maybe that's Kelvin-Helmholtz unstable. And this paper by Hoffman and Thompson 2011 is the first reported observation of the KHI in these coronal mass ejections. And they've got a few images over here from this picture that they took of things that they think they see that are the Kelvin-Helmholtz instability. And I'm not wholly convinced, but just by these images, and I made a circle over here on the bottom right. Maybe something like that is the KHI that they were looking at, but it's not, visually is not the only way that you need to that you can use to figure out if this is the KHI or some other order instability. You can do the math and the physics theory to back out things like the frequencies or the growth rates or the energy cascades for these instabilities and how they're expected to form. But more recent work from the Parker Solar Probe, which I want as a quick aside, what a cool satellite that we developed. It's the closest object that's been ever put to the sun, and it's the fastest human-made object ever. So Parker Solar Probe is a testament to human engineering. But there was a coronal mass ejection, and they actually made a really great observation of the KHI. It's hard to see in some of these, But these arrows point to the different vortices. This one does a really good job. You can see these bumps over here that are all KHI vortices caused by because of a fast ejection moving around some past some not moving plasma. And what I find really fascinating about these is that uh, these actually kind of look very similar in shape to the clouds that we saw over Hartford, Connecticut. So I find this another really neat way. Like these are on this probably on the scale size of like the Earth or something like that. And these are and we're looking at clouds on Earth. So just the different scales that we're seeing the same general sort of behavior happening is really neat. So if we go away from the sun a little bit, we can see that the KHI can also occur in comet tails. This is actually just a beautiful picture I happened to stumble upon on the internet. This is a picture of Comet Lemon, which passed near the Earth last year. And we can see for the exact same reason, the comet is moving, the tail is a bunch of plasma, and it's moving with respect to the ambient plasma around it. And we see these unstable waves due to the Kelvin-Helmholtz instability happening on the tail, which is really neat. So it happens in planets, it happens in stars, it happens in comets in our solar system. Let's look a little bit further out, right? Let's look outside of our solar system. Let's look at galaxies. Here I have the N1404 galaxy, which is an elliptic galaxy, and it's moving generally to the top right. And this galaxy is in motion with respect to its intergalactic medium nearby. So because of this, we think that this might be unstable to the Kelvin-Helmholtz instability. So I want to point out the scale here. It's 20 kiloparsecs, just to get an understanding, just the huge breadth of space that we're looking at in this image. This is an image from the Chandra X-ray Observatory that we're seeing here. So we can see that the KHI can occur on all these different scales, and it can manifest in multiple ways. So on the left here, we have on the leading edge, there are some of these terms over here, these little ripples that they think. Okay, now I want to give the caveat. Galaxies are much harder to observe than planets that we have satellites orbiting or satellites going by. So we have to make a lot more inferences. So the pictures for some of these galaxies are going to be as beautiful in terms of the instability development, but there are indications that these instabilities are developing near these galaxies. So there's these the KHI eddies that are occurring on the leading edge is very similar to the steam I was showing in the kitchen. Like it's moving in one direction and then it causes motion around it, inducing those Kelvin-Helmholtz vortices. On the right here, we have on the top right, I have a different galaxy, the NGC 4649. It's also an elliptic galaxy, but we can see this weird like structure on the top and bottom. It's also moving to the top right. We can see this weird structure on the top and bottom. And the question is, what might be causing that? And one hypothesis is it's also the Kelvin-Helmholtz instability. On the bottom is a simulation of a different galaxy, the NGC 4552, but it's a very similar type of galaxy. So in this case, it's moving to the right. And in this simulation, you can see this like winged structure. Now that I look at it, it almost looks like a fish. But yeah, you see this interesting like winged structure happening on the top and bottom, and that's because of the Kelvin-Helmholtz rolling up around it. And we can so there's some similarities between the two. So the KHI can show up on galactic scales, which is really neat. So let's go even larger. Galaxies can be bound to each other gravitationally and form galaxy clusters. So this is an example of A2142. Is an ongoing merger of two galaxy clusters, and this is actually one of the largest known objects in the universe. And much like before, this has a relative motion between itself and the medium around it, and this might cause the KHI to form. So you can see some of these little bumps over here are indicative of things that might be the KHI. Let's just take that idea in, right? The same thing as waves on the beach is creating these gigantic waves in galactic cluster scales, and in these galaxy clusters, you've got galaxies within there that are moving in this wave-like pattern. In a galaxy, there's whole star formations and solar systems moving in these wave-like patterns. So, yeah, it's just really fascinating, neat thing to consider in terms of how mundane things that we see are the same things happening in space. So let's change gears a little bit and look at a different instability called the Rayleigh-Taylor instability. This is an interchange instability. So you'll basically what that means is two things are going to want to change spots in a sense. When you have a heavy fluid on top of a lighter fluid, and you require some sort of acceleration, which on Earth that for us is going to be gravity. Uh, so let's go back to an example of, if we look on the bottom left, is something that we probably all did as kids as a science experiment. You had oil, water, and syrup, and they all settled to their own different locations because they were all at different densities. Now, we could think of this as the bottom of our pendulum. This is our stable equilibrium. What if we flipped it upside down? This is the top of our pendulum. If you have it perfectly set up with no perturbations or anything, this should stay as is forever. But once you add a tiniest little perturbation, the syrup is going to want to come down, the oil is going to want to come up, and that's what the Rayleigh-Taylor instability is. So here is a simulation of the Rayleigh-Taylor instability. The first part we get the linear phase, and then it continues to go down, and then we get this like a hammerhead or mushroom type shape forming in the third panel, and then as we keep going further, we see these interesting things begin to form. So if we have one heavy fluid going down and a light fluid going up, we have a velocity shear. So can I ask the audience, what do we think might occur over there? Yeah, KHI, Kelvin-Helmholtz instability. And that's exactly what we're seeing over here on this side. We can see these secondary Kelvin-Helmholtz instabilities develop. But then the bottom, you still have a heavy fluid going down, and there's still light fluid under it. So you end up with secondary Rayleigh-Taylor instabilities forming. So in a very similar way to the other simulation I showed of just the KHI, we get this really rich instability structure that develops that in these highly nonlinear, highly complicated ways, and understanding how some of these energies cascade down is very useful and important for many physics applications. So I'll come back to the audience. Where do you think you might have seen this instability in your life? And I'll give you a hint. This is the part of my talk that's related to the title of my talk. Coffee, yes, coffee. So for those of us that like to drink coffee, specifically with cream, if you like your coffee black, you may have never seen this. But if you like it with cream, here's a video that's playing right now. The act of the mixing with the cream induces the Rayleigh-Taylor instabilities. Now, this happened very quickly, but all the different wisps and the little like light-dark changes are the different Rayleigh-Taylor instabilities that are being induced as we pour the pour the cream into the coffee. The cream is heavier than the coffee, which is resulting in a Rayleigh-Taylor instability. So now I'm going to play just the same video again, just slow motion, because that one was really fast. So if we go a little bit slower, it's starting. Hey, here it goes. Yeah, hopefully you can begin to see some of those different instabilities develop. It should stop. Okay, yeah. So over here, you can maybe see there's like a wisp over here, there's a wisp over here, there's a wisp over here. These are all different Rayleigh-Taylor instabilities, and if you look at like the light, the dark, the light, the dark, that's the different like the banded structures that we see for the cream and the coffee as they interchange and change their spots. And then the kind of the stable equilibrium here is that that all gets mixed together, and we have a nice cup of coffee that is cream and coffee, and not just one and then the other, right? So, okay, it's just playing again. Okay, it's this rest of it. Another example of the Rayleigh-Taylor instability is in explosions. Here is an example of a nuclear weapons test back in the 1950s when the United States was still doing these nuclear weapons tests. But this works really for any sort of explosion, as you end up with the explosion happens, it heats the air directly near it. So now you have hot air, which is less dense than the cold air above it. So now you have heavy air on top of light air, so it's going to interchange and it's going to create the Rayleigh-Taylor instability. And the simulation I showed was kind of like an upside down version of this mushroom cloud type of thing that we were seeing before. And this happens in these sorts of, like human-caused explosions, but it also happens naturally. Here is a picture from the ISS of the Sarychev volcano in Russia that erupted in 2009, and we can see the same exact sort of behavior from a purely natural phenomenon occurring for the exact same reason as the other explosion. So we see this as well in all sorts of other places in the universe. So let's go back to the sun and look at a solar prominence. I showed a very similar picture to a video to this earlier, but this is a solar prominence very similar to a coronal mass ejection. The coronal mass, it might end up leaving the sun, or it might just go back in and become part of the sun again. But when you have a configuration like this, you could have situations where you're actually Rayleigh-Taylor unstable. So here I'm going to be playing a video. I want us to focus on like the bottom part of this video, and you're going to be seeing all these bubbles pop up that are going to look like the Rayleigh-Taylor instabilities that I've been showing. Yeah, so hopefully we can see some of these bubbles pop up. They bifurcate a little bit. They can have some of the hammerhead structures. So and this is also just very like mesmerizing to look at as well. So we can see that the Rayleigh-Taylor instability is something that occurs in a star during its regular life, like our sun, but it also occurs in stars in the end of their life. So it can occur in a supernova. Our sun is probably not going to do this, but the way that stars balance themselves hydrodynamically is that there's the inward push of gravity that wants to continue and collapse the star. But then in the center of the star, there's nuclear fusion occurring, and that creates enough energy to keep it out. So that gives the star its shape, generally circular, and prevents it from collapsing in on itself. Eventually, when the star's core starts fusing iron, it doesn't have enough energy to maintain that balance, and you end up with a situation where you might have the star implode all the way because it can't hold up its own gravity anymore, and then it explodes into a supernova. During that explosion, you have this heavy plasma that was inside the center of the sun that now gets pushed outward towards the lighter plasma that was the outside. I shouldn't say the sun, star, because in general, outside of the star. And that might induce the Rayleigh-Taylor instability. So we can see here is a false color image of a supernova, and we can see like these little bumps inside that are possible Rayleigh-Taylor structures. So that's really cool. So now let's fast forward about 1,000 years. So here is the Crab Nebula. So 1,000 years ago, this Crab Nebula, in this nebula, there was a star that became a supernova, and that star became a pulsar, which is a rotating neutron star. So as this star is rotating, it's pushing all these heavier particles out into the rest of the supernova remnant, and it creates all these really interesting Rayleigh-Taylor patterns. All these different wispy structures that you see, and some of the different hammerhead structures that you see, those are all different Rayleigh-Taylor instabilities that are they're existing in the Crab Nebula over here. So really, like the full like life cycle of a star, because there's stars being born in this nebula, or the full life cycle of a star from birth to death and life. Rayleigh-Taylor instability is all over that, which is really neat to think about. So I talked a lot about how we can see this in our regular lives, how this shows up on all these grand astrophysical scales. I want to talk a little bit about, how do they affect us here on Earth from the perspective of why do we care about learning about these instabilities, and beyond just it's cool to learn about things because it's there, from the perspective of like, how does it actually impact us in sort of applications in engineering and things in our lives. And this is some of the work that I did. This is actually a direct plot from my PhD dissertation. So I study plasma instabilities in the ionosphere, and it's very important to understand these because these can disrupt GPS signals. Is the biggest reason. So on the top left, we have an image from the Australian Bureau of Meteorology, and if you have some sort of communication signal, and when we speak to the GPS satellite, we have to send a radio wave to that GPS satellite, and if you have plasma turbulence, plasmas are charged particles, that radio wave has to go through that, and it degrades the wave a little bit, so we lose some sort of certainty of where our position is. Whereas before, maybe we knew that we lived in this little bubble. Now we know that we live in a bigger bubble, so it becomes a problem. In 2024, there was a large solar storm that induced so many different plasma instabilities, and it disrupted GPS, and it resulted in planes getting rerouted. It resulted in a lot of issues in our agriculture. We're mechanizing a lot of our agriculture, and tractors are becoming automated now. So they actually, like trampled over their crops, and there was actual realizable crop loss and economic loss. So it's very important for us to understand these sorts of instabilities, so that I don't know anything about the radio propagation of it, but then if we understand the plasma physics, then maybe someone can take that and improve our communication signals to make sure we don't have to worry about these sort of natural events that are always going to be occurring, affecting our lives. So some of the key work that I did in my dissertation was looking at how different altitudes we might get different instabilities form in the same general sort of ionospheric formation. Uh, on the left here, we can see that there's a Kelvin-Helmholtz instability forming. On the right here, there is a Rayleigh-Taylor-like instability. This is an instability that's called the gradient drift instability. It's very similar to the Rayleigh-Taylor, um, in that it's an interchange instability, but it's formed due to the combination of electric and magnetic field effects. And in the middle, which is kind of like a middling set of altitudes, so KHI is happening at high altitudes, GDI or RTI is happening at low altitudes, and it's a middle set of altitudes, we get some interesting combination of both of these instabilities. This was kind of like the big finding that I had for my PhD work. And what's really neat is now I'm trying to work with the Johns Hopkins Applied Physics Laboratory to see if we can actually send a satellite mission out there to validate this hypothesis and look at a highly eccentric satellite orbit. Maybe we could check out several of these different altitudes to see if we're actually seeing these different sorts of instabilities form at these different altitudes. And uh, the other application I wanted to talk about is with nuclear fusion energy. Now, I don't work in this aspect of nuclear fusion energy, but this is the one that has the coolest pictures when it comes to these sorts of instability. So I'm going to be talking about this one today. Uh, Pretty much every nuclear fusion concept has has the issue of trying how do you confine a plasma. It's very difficult to keep a plasma in one spot to get it really hot and really dense to mimic some of the way that the sun does its nuclear fusion so that we can harness it in a safe, reliable way to make like an actual realizable power plant. This is a method called inertial confinement fusion. So we could think of it as kind of like making a mini controlled supernova. So you have a little pellet that might be actually like this big, and it sits in this chamber here. Those are like those are people to give you a understanding of the scale of this facility. This is the National Ignition Facility, and there's all around it is all these lasers that are pointed in at that one little small pellet. Inside of the pellet is a deuterium-tritium mixture, where those are two isotopes of hydrogen, and the goal is if you can spherically symmetrically compress the this pellet, you can end up really increasing the densities and temperatures in the center, and you can induce some sort of fusion reaction over there. And hopefully, then we can take that and harness that and create some sort of actual realizable energy out of it. But this issue is plagued by plasma instabilities, and this is really a huge area of research. And like, how do we mitigate this? Because if we lose that spherical symmetry, well, then we're losing some of the energy that could be going into the center part of the plasma, and then we're no longer maintaining that efficiency, and we're not going to actually get enough energy out of it. So, and this is actually one of the cases where you can model a solid as a fluid. The pellets are made of like solids and foams, and they just get these really large compressive forces from all these lasers. So over here we have some actual images of these are actual Rayleigh-Taylor instabilities that are occurring on the solid outsides of these pellets. So that's like the linear phase, and this is the nonlinear phase here, which is the like the hammerhead structure of those Rayleigh-Taylor instabilities. And this is a bad thing, because you could think, how much energy is going outwards radially over there when we want all of it to stay inside. So there's a lot of research being done right now in terms of how to mitigate these sorts of instabilities, and there are a lot of different interesting ways to do so. So with that, I want to thank you for your time, and I just want to bring it right back to this really cool thing of how regular everyday life things like coffee and this cup over here and the cream mixing into it can look very similar to the Crab Nebula and things on very large astrophysical scales. So hopefully I've conveyed some of that to you today. So thank you for your time, and are there any questions?
All right. Thank you so much for another great talk. So, before we get into that, because I believe there were a couple people who snuck in here after I gave the safety briefing, just a reminder, if you guys need the restroom, that is the porta potty in the back. To my left, your right. We also have a little museum and gift shop area. Also here in the door outlined with red. Each of the sheds out there you passed with the roll off roofs houses its own telescope, and the ones with the roofs rolled off will be open for stargazing. So far, it looks like we do actually have sky and not just solid cloud cover, so that's looking good. A reminder, when we go to leave in our cars, we are using headlights. Headlights are good, they help us prevent trips to the ER and unneeded medical bills. And any flashlights, since it is starting to get dark and it will continue to get dark, we do ask the flashlights and whatnot be kept pointed towards the ground when possible, just to avoid blinding people. Now, for Q&A for the people here, I have no night vision. I've been staring at a screen monitoring chat. So if you have a question, when I call for him, you're going to raise your hand and kind of wave it about like you just don't care. Because much like the Jurassic Park T-Rex, my vision is now based on movement. If you put your hand down, you will just kind of fade into the darkness as a shadowy figure. Unfortunately, that's just how my vision works nowadays. That being said, online people, you have it easy. You get to type. I'm going to start this off with our first online question. I'm going to actually do this one. And I'm going to clarify again, this is not a dumb question you asked because you don't know unless you ask or someone happens to randomly tell you information. Space does not have friction, correct? Is there increased stability in the analogy because of the friction and pressure as the fluid compresses at the front?
If they're talking about the supernova, then there is a lot of stuff there. So let's answer the question kind of broadly. Everything has friction, uh, but space has much less friction just because there's less stuff there, right? If we think about it from the perspective, if we wave our arms a lot, we can feel the air around us. That's because our hands are hitting the air around us. Now, if you did that in space and somehow were able to stay alive, you wouldn't feel as much stuff, right? But there is still some stuff out there that you might feel. Maybe when you look at these large galactic scales, you'll start feeling some of these things, and that's why we can um, model all these different things as fluids. When it comes to looking at the thing with the compressive effects versus the supernova, uh, it's that in supernova, we see the Rayleigh-Taylor instability because that's just what nature does, right? Nature doesn't care about what we care about or what we want to do. We see the Rayleigh-Taylor in the supernova. On Earth, it's very much similar to what's happening. It's just it naturally is something that occurs, and we have to figure out how to kind of defeat nature in that respect of, okay, how can we play with this a little bit differently to engineer it in a way that we don't see this instability develop. Hopefully that answers their question, if that was my
I
interpretation
hope
of
so
it.
too. If that didn't answer your question, feel free to clarify in chat because you are unfortunately limited by my understanding and ability to convey your question. Right. Any questions out here? I hear crickets, which is good since we're in a state park. We should have crickets. Um, all right. So I'm going to get our next online question, which is, aren't gases technically also affected by gravity? Otherwise, atmospheres wouldn't be as much of a thing?
Yes, gases are affected by gravity. They're just affected generally less. That's not even true. They're affected less by gravity from the perspective of there's more stuff underneath it to kind of keep it up. There's whereas right now, like I've got my water bottle and I drop it, it just falls. But if I had something that was kind of similar density, there's enough stuff pushing up on it that will keep it in its same general spot. So that's why we see. So yes, gases are affected by gravity, but kind of in the space that we care about. If I have like some jar of air, it doesn't change very much. But when we look at it from the perspective of uh, actually as you go up in space, as you go up in altitude, there's a reason I was showing in that one slide that the mean free path got larger and larger because there's less stuff up there because there's less gravity to keep it bound to the planet. That's why you need to bring oxygen masks and stuff at the top of mountains.
This is also why when people are going like caving or doing work in the ditches on the side of the road, or doing any sort of excavation where you're in a hole, uh, they have to be very careful and monitor because different gases, different densities,
Hmm.
and they settle to the bottom. Like carbon dioxide is lovely and heavy, and when you get into a cloud of it, suddenly you have no air and it's very hard to breathe.
Yeah, another
So
big one is radon. Radon's a very, very heavy gas, so you could end up in situations where in like mines and whatever, you just got a pocket of radon and there's displaced the oxygen eons ago. So yeah.
yeah, I found out about the carbon dioxide the hard way because one of the soda fountain machines in the back of the restaurant I was working in uh, was just leaking carbon
Oh
dioxide.
no.
Went into that room, went to go change the bib, and go, I can't breathe. So yeah, it is in fact applicable to real life. Checking. Any questions? Like I said, if you have a question, we got one.
Okay, so my question is about so with a lot of like the KHI like
Hmm.
instability that we showed like the examples like with the waves and like the coffee, it was because of like a desire to bring back stability. But my understanding with the universe is that it's expanding at like an accelerating rate,
Hmm.
which means more chaos. So I guess I'm trying to understand like what is the end effect of all those instabilities happening in the universe?
The end effect is that uh, uh it does end up into a more stable regime.
Okay.
So what we're looking at is small scale things in the giant scale of the universe. So on the large scale, the universe is kind of trying to, uh, there's like the idea, like the inevitable heat death of the universe. It's trying to eventually make its way to some like large scale equilibrium, but we're not there yet, and we're very far from it. Thankfully for us, right? Uh, in that in this time scale, what we're looking at is these small different instabilities that develop, that then individually in that local region, now maybe it's gone into some sort of more stable state. You could think of it as a good example is, right, we've got all these mountains and whatever, but we don't always have rock slides, right? Why doesn't it all just come crashing down? Well, it does every now and then when there's an earthquake or something. The Earth will eventually make itself stable, but it's in much longer timescales that we don't need to worry about. So hopefully that sort of analogy helps with your question.
Yes, thank you. I
Yeah,
appreciate it.
All right, our next online question is um where did it go?
it's
There
a
it
good
is.
question.
Uh didn't they determine glass to some extent to be a very, very solid fluid? Glass.
Yeah, I know what they're talking about. I think it's considered somewhat of like an amorphous solid. Uh, I haven't looked at that in some time. I feel like I heard that a long time ago, and then I also read a few articles that it wasn't actually that the glass itself was an amorphous solid of that. The reason was that when they looked at old glass from a long time ago, it was thicker on the bottom and it was thinner on the top. Uh, I feel like I read it, so I don't quote me on this internet now that I'm going to be forever on the internet. But I feel like I read an article that showed that it was actually more of just the method at the time of how they made that glass made it such that at the time it settled so that it was thicker on the bottom and lighter and thinner on the top. So it was less that it was all uniform and then it made its way down, um, and more that that was just the way that they had to manufacture glass at the time. But yeah, it does have a slightly different crystalline structure, or maybe lack thereof. I'm not a solid state physicist, so I don't
Yeah,
really
I,
know.
I feel like that would actually be a good question to go try and stump some of the more um not that your science isn't practical, but more of the hands-on practical science people. Or if you're ever at like a Renaissance fair and they have the glass blowing demonstrations, go see if you can stump them with the fun science questions.
Hmm.
Oddly enough, they actually know a lot of their stuff. It's just they're usually in entertainment mode, so sometimes it's fun to switch paces for them. All right. Yes, Kim was over there in the background battling to keep wildlife out of the house and museum area. I just wanted to clarify that. Any other questions out here?
All
All
right.
right, one all the way in the back. I have short little legs.
You were talking about plasma instabilities affecting GPS
Yes.
coordinates, farm tractors.
Yeah.
Is there a way to predict them? Do we have 10 minutes to act before they hit? A half hour, or they still just come randomly and we have no idea?
We have yes and no. We have a way to predict them on like larger scales, but we're still figuring out how to predict like a localized effect. So we have all these different satellites and things that are monitoring the sun, and we know, so when we have large activity from the sun, like that coronal mass ejection that I showed, right? If that happens to be going in the direction of where the Earth is, then that's going to make its way, hit our planet, and all of the plasma from the sun is going to rain down into the planet in some way and induce all sorts of this turbulence and these instabilities. So we have an understanding of, we know that it's coming, but we may not know necessarily where it's going to end up on the planet. So it might end up at the poles, it might end up in certain different other latitudes and other locations, depending on the timing and the strength of all of that. That's the big aspect of research that we're still looking on. I'm not really working in any of the large scale predictive stuff, but that's really one of the big areas that a lot of the field is looking at, is how can we actually then do actual weather like space weather forecasting, to then say, okay, you know what, maybe like one method that I've heard is, if we know that there's going to be a patch of instabilities over there, well, we can either, maybe we talk to another satellite over here, send a signal that way. But if we still need to talk to that satellite there, the signal goes there, then the satellite sends a signal, outside of Earth to that other satellite, or some sort of concept like that. But we're not there yet. That is the goal. So yes, on a large scale, we know it's coming. It's on a small scale, we don't know exactly where specifically it's going to be yet. There looks to be a follow-up question.
The question was, how often do they occur?
That's a good question. I don't think about that very often. They occur often enough that we need to worry about it. This particular one that I talked about in that happened in May of 2024 was a rarer event, so they don't occur that frequently. But there is like a solar cycle. Every 11 years, the sun has like hot spots and cold spots, of like that's not even the proper word, like high levels of solar activity and low levels of solar activity. And I don't know what's going on in the sun to do that, but we can kind of get some sort of prediction of, okay, in a high level of solar activity, we might expect more of these. In a low level, we might expect less of these.
Uh,
Yep.
That cycle is actually called the Saros. We had a talk in the past. We don't have it scheduled this year, but you can look up that talk on our YouTube channel. I know it's there. I forget what list you need to click down into, but I swear it's there. So if you're ever like, hey, I didn't think of that, we do save all those talks on our YouTube. Our next online question was, regarding the mean-free path, why is it easier to model fluids that play bumper cars with themselves more than stuff that is less likely to?
The reason is because if the more bumper cars that they play, the more averaged out their statistics are going to be. So we could think of it as the more bumper cars that they play. If you remember, like the normal distribution that you might have used in like your statistics classes, the more likely they are to follow a normal distribution, because they're bumping into each other. So on average, they're going to end up with a similar sort of sets of behavior, then because they have that similar set of behavior, you can use that to not have to look at each individual particle and say, okay, because they're all following a similar set of behavior, I can look at this larger scale statistical quantity and model just that. So that's why you want them to collide a lot more frequently to be able to model this as a fluid. Because really, the modeling of a fluid is saying if we have a statistically large enough sample that is a similar sort of shape in terms of the distribution of how the velocities are, then you can model this as a fluid.
Right. Uh, the person who had asked that first online question, uh, said, "Cool, they didn't know space had friction." And a follow up: do you have any recommended further reading for research into controlling the instabilities in fusion processes? They're not a physicist, but they think it's neat.
I don't know it from the perspective of a not like I can send you a bunch of plasma physics textbooks your way, but I don't think that's going to help you.
I don't know. It might. You got to start somewhere.
Yeah, I mean, it doesn't have a lot of the instability stuff or the controlling of the instability, but the plasma physics and controlled fusion textbook by Chen is kind of like one of the best ways for people to learn plasma physics. Every grad student usually uses that one. So there's some talk of the instabilities in there, but also it provides a good foundation into some of the other stuff of what's going on in plasma physics because there's aspects of trying to understand the controlling and mitigation of the instabilities where if you have somewhat of a foundation in the plasma physics, you can then begin to understand more of the high level details. But yeah, this is plasma physics is not really something that's taught outside of graduate level courses really. So there sadly isn't as much. I'd like there to be more, but there just isn't as much things to give to the general public to help to talk about the science in that way.
You'll have to think about it, and next time you give the talk, you'll have a reference section.
Yeah, I'll
at
have
the
a
end.
reference list. Yeah, yeah.
And like with ISBN numbers. Actually, you could probably when this is saved, go on and comment the
yeah.
name of the textbook and
Yeah.
the ISBN number so they can find it.
Mm-hmm.
Because unfortunately, AI does weird things now and is writing some textbooks, and it looks like the right one, but it's not. Found that out the hard way. All right. Any last minute questions out here? Also, you had mentioned I'm making an assumption, and you know what they say about assumptions. You were asking about Professor Lindsay
Oh yes.
Goodwin. I believe she was in here because Professor Lindsay, the space wizard, so she was watching you.
Oh, cool. I didn't know she was a space wizard. That's my boss.
I didn't know either. Again, I'm making assumptions. So if you are not the Lindsay I'm thinking of, I'm
that
sorry.
sounds like her.
Right. So online people, any last minute questions, do get those in. We will try and get them answered. I just would like to give you guys a little bit of a minute because of the fact that by the time they hear it, we're already a couple minutes into the future. We're special like that. No, that's how stream delay works. We are not space wizards who can travel through time.
Then we'd be time wizards.
Space, time, physics.
Yes.
Physics. This is not a Doctor Who episode. All right. Someone also had said this feels like something from getting their ham radio license on how different layers affect wave propagation.
Yeah.
So, do you work with the ham psi?
I do not, but there are other people at NJIT that do. But yeah, a lot of looking at radio wave propagation is trying to understand how different layers of the ionosphere are going to affect your radio wave propagation. I don't know how much the turbulence plays into it, but a lot of the way that radio works, and it's really one of the ways that we discovered the ionosphere exists, is a long time ago. I don't know what the name of the scientist was, but they tried to send a radio wave from one location to another location over the horizon. And the problem was we didn't know there was an ionosphere because the way that it works is you send a radio wave up into space, but because there's a plasma density, when your wave hits a particular plasma density, depending on the frequency of your wave, it's going to bounce back down. Uh, at the time, the person who did this test didn't know that, so they sent a wave over the horizon. So normally you wouldn't think you can send a wave over the horizon because it has to bounce around the planet somehow, but they did, and they're like, "Oh, this is cool." But then afterwards they realized, "Oh, we did that because there's all this plasma that's living up in the near Earth space environment." So that's actually how we discovered that the ionosphere exists, is by sending radio waves out, and we were confused. Oh, why are they coming back?
This is not weird radio echolocation, although I guess it could be.
That's what radar is.
Yeah.
Yeah.
Yay! I learned something. Yeah, this is the fun part. Very sciencey people. Very not sciencey person leading the talk. All right. So it looks like that is it for the questions. I want to thank everyone for joining us. Like I said, everyone here, feel free to peruse our telescopes, peruse our museum area. Online people, thank you. Hit those like, follow, subscribe buttons. The free actions are great. And if you're feeling extra generous, like I said, we are doing a fundraiser to get us across the finish line to building the observatory for the 25-inch Midkiff telescope. With that, thank you, Chirag, and clear skies and good seeing, and see you next week.